Alright, so we're going over 3.3 derivatives of logarithmic and exponential functions. So first, it's important to note that a logarithmic function is continuous on its domain, and that's typically going to be um, um, all or x greater than 0, not equal to 0 because log 0 is undefined. So it's differentiable, and the form that they'll typically give you is f prime of x equals 1 over x log ae. Well, interestingly enough, you can apply the change of base formula here, and they use ln e over ln a, just equal to 1 over ln a, such that the derivative of any logarithmic function is equal to 1 over x ln a. Pretty important, pretty easy. And the beautiful thing about this is you can use logarithmic differentiation to prove the power rule, which I didn't know. I mean, I thought they used binomial expansion theorem. But I guess this is so much easier. And maybe it might not be the formal proof for the power rule, but it's still a pretty intuitive proof. So we're going to take this right here and we're going to apply it to ln x. So ln x is just the same as log ex, so you just apply the derivative, which is just going to be 1 over x ln e. Ln e is equal to 1, so it's 1 over x, and that's the derivative of ln x. Pretty simple. So now this is just going to be extrapolation, so we're going to take ln of x cubed plus 1. And as we know, it's just going to be chain rule, so it's going to be 1 over x cubed plus 1, not changing the input, times the derivative of that, which is just going to be 3x squared. And you can simplify as needed. So yeah, that's all that is. Now let's go on to what happens when you do a piecewise function. And it gets a little bit more tricky. I mean, it's not tricky. You just define your boundaries. So you can set it up as a piecewise. A lot of people like to define absolute value of x as the squared and then the square root, because the squared eliminates the negative and the square root eliminates the squared number, but it's okay. So the piecewise is going to be ln x if x is greater than 0. So pretty simple, and it's going to be ln negative x if x is less than 0. Also, I probably shouldn't put the equal sign because it can't equal 0. The reason why it's ln negative x is because when you plug in a negative numbers, like on the Cartesian coordinate plane, if you're right here, negative times a negative, or the negative input here times the negative here becomes positive, and then you could take the ln of that because it's the same thing as absolute value. So all you do is logarithmically differentiate both sides. Here's just going to be 1 over x if x is greater than 0, because that's an elementary derivative. In other words, we don't have to do anything here. Here it's going to be 1 over negative x, and then you chain rule the inside times negative 1, which is just equal to 1 over x if x is less than 0. And also no equal signs. And obviously we know that this will be a negative rate anywhere on the left, because anything less than 0 is a negative number, and 1 over negative is going to be a negative rate. Pretty simple there. Now, logarithmic differentiation is really the most beautiful thing I've ever seen in my life. So we'll take a function, the y equals x to the 3/4 times x squared plus 1 to the 0.5 power, and then 3x plus 2 to the 5th power. So before we know this, we know that log rules state that you can split products and quotients quite easily. So ln y is going to be equal to ln. Remember, we can just pull the power out. It's the rules of logarithmic, the logarithmic rules. And for products, you can just add it. So it's going to be 0.5 ln of x squared plus 1. And for quotients, you subtract. So it's going to be minus 5 ln 3x plus 2. And what we're going to do is we're going to differentiate implicitly. So here it's going to be 1 over y times y prime, because we don't know what y is as a function of x. We technically do. It's this right here. So I can differentiate this, but this is what we're trying to find. So just implicitly differentiate. We know what y is. It's just this entire function. And you just differentiate this side, which just becomes 3 over 4, 1 over x plus 1 over 2, 1 over 2 x squared plus 1, and then 2x right here, simply because you differentiate the inside and chain rule it, minus 5 minus 5, 1 over 3x plus 2 times 3. So simplifying this out, it becomes, well, before we do, let's multiply y on both sides. So if we multiply y here, we cross this out, and we just multiply this entire thing by y. And coming back up to the top, just to add more space, it's going to be equal to y is equal to 3 over 4th x plus x over x squared plus 1 minus 15 over 3x plus 2. And remember that we multiplied y at the end. And we're not going to simplify because that's practically impossible. I mean, it would just take a lot of work, essentially. Square root x squared plus 1 all over 3x plus 2, and that is derivative. I'm sure you can simplify it even further. In fact, like if you did the product and quotient, it's a lot easier than doing product and quotient rule. In fact, like I hate doing the quotient rule. It's just so much work. But then you have to mix it with the power rule, and that just gets really messy. So yeah, that's that. Now we have a proof for the monomial power function, which I'll also separate in another function or in another video. But y equals x to the n. I mean, this is such a beautiful proof because I tried so long trying to do it with combinatorics, and I hate combinatorics because it's pretty abstract to me. But anyways, we're going to prove that y prime is equal to nx n minus 1. In other words, the power rule. So we'll start with y equals x to the n. Then what we're going to do is logarithmically differentiate both sides, or log both sides, or len, I guess would be the proper term. Remember, you could just pull the n out front. This is going to be 1 over y prime if we implicitly differentiate both sides with respect to x. And that's just going to be n 1 over x, which is just the same thing as n over x. So that means y prime, and we'll just times y on both sides, is going to be equal to n over x times y. And remember, y is just x to the n, so it becomes y is equal to n over x times x to the n power. And this is the power of 1, so you could just subtract it from the top using our exponent rules. And that is the beautiful thing about that. So, I mean, that's really beautiful. Now we get to exponential functions. And this is also extremely beautiful because we have the function here. And we'll do the d over dx ax. So any base raised to a power, any base raised to a power, or any base raised to a variable is equal to, the derivative is equal to ax, l, and a. So that means if we take the derivative of Euler's to the x power, we get Euler's x to the ln Euler's, and this just cancels out because it's 1. Now, what I like about this is that you can infinitely take the derivative of Euler's to the x, which is an infamous derivative, and you'll always get the same thing back. And if you want to conceptualize it using physics, that means if you're traveling at a rate of Euler's to the x, that's how much you move. So like, let's say you move 20 meters, then you're also moving at a rate of 20 meters per second at that instantaneous point, which is quite genius, actually. And pretty cool to understand. So now we'll just do a practice problem of y equals Euler's to the 10x. And the reason why we're doing this question is because it's power chain rule. Not power chain rule, it's just chain rule. So we take the derivative of this, which is just the same thing because there is no derivative of that, times the inside function, which is secant squared x, or the derivative of the inner function. And so that's that. And then I guess the derivative of the input, which is changing linearly at a slope of 1, so it's just going to be 1, I guess. You don't even have to apply the chain rule because we know we're differentiating with respect to x. So that's it. And yeah.